Howdy, folks. So, got time for more chatting about code, about computer science topics, about technology, whatever is of interest to you. I have a plan for tonight, because you know what I haven't done in a long time is write a hash table. And what I have to do here in the near future is write a fairly specialized hash table for some of my research. I figured I might want to actually make sure that I'm still decent at hash tables. I've taught them relatively recently, but I don't think I've written one. Well, that's not entirely true. Hey, why'd you switch to the other Emacs window? It's not entirely true in that I have... Stop that. This window. I have taught about hash tables, and I guess I wrote one in Java not too long ago, but it was not the most advanced hash table. And I'm gonna have to actually write a decent sized one. So let me start this off with a file. For some reason it's wanting to show the same Emacs twice instead of two separate ones. Alright, so let's do this just, I don't know where we do it. Let's do it in just like a temp directory. And we're gonna hash table dot H. Sure. And to add to the challenge, I'm gonna try to work on it in C++, because that's what I'm gonna need to write in for my other one that I'm gonna have to write that's sort of specialized. I don't know why it's doing this. It's exclusively letting me only choose that one Emacs window as a display. But as it says in the description, you bring any question you got, any topic you got, be glad to talk about whatever concept might be on your mind. All right, I'm going to shuffle stuff around in a minute because this is for some reason not showing up right. But you can join the queue and just add your topic, your question to the queue if you want. And that is with the join command. So we're gonna kill this one. Gonna unkill this one. And we're gonna shuffle around a little. Sorry for moving everything on you while you're hanging out, but it'll be just a moment. I don't know why it was not letting me have the second Emacs window, but you get more of me now until I have something else to show off, and then we'll move stuff around. All right, so let's talk hash tables. You may be familiar with the basic idea if you've worked in something like Python before. Dictionaries are a hash table. All you really need is like some idea of what's going to be a key and some idea of what's going to come out as values. And if you really want to be strict, then your keys in a hash table should really always be integers, and your values will be whatever type you want them to be. It's not updating in the display there. That is weird. I don't know what's going on with my Emacs windows tonight. And it keeps wanting to switch to the browser no matter. Hey, look, it updated. Now does it update? Yeah, now it's tracking. Okay. So, thinking about writing a hash table, I'm going to try to keep it relatively simple and then maybe build from there. So, the trouble with hash tables is you want them to be quick, like an array. In an array, you've got keys and values. They are integers, and they're whatever data type your array holds, right? So you could have like an array that holds strings, and each string goes at one location in that array. They all get their standard length for them. That, whatever you want to put in that array, you can put it there. Car, sat, whatever. So an array is kind of like a hash table, but a hash table is going to allow you to put them in based on some important information that is connected to the data. So that if I ask you, where's cat? You'll be able to look at cat and somehow conclude what the location would be in your hash table. Here, for instance, these aren't even sorted. Even a sorted array, this doesn't work because you still don't necessarily know that if I ask you for boy, is it the third item? Is it the second item? You'd have to know all the other items. So what we do instead is we hash them. We take something like cat, and here's a bad hash for cat, is we could take each letter in the word and we could turn them into a number. So we could say that like C is 3 and A is 1, right? 1, 2, 3. And T is good Lord, whatever T is in the, here, let's do this. I can't remember. Anyway, whatever number T is in the alphabet, you can say that T is that. Let me. Anyway, you can take those, add them all up, and you can make that a hash, right? You can take each letter and add them, and when I figure out what T's number would be. Oh, you know what? There is an alphabet in Python. Python get. What is it? String module. Why am I playing with this? Why am I doing so much work? Here we go. Dot index. Is it find? I think it's find in Python to get something from a list. 19. Which would make it 20 in our numbering here because I bet A counts as 0, right? In that one. We could also do this the 0 indexed way and make AB19. I'm sorry, AB0, TB19, and CB2. But the problem with this is, then let's say we have the string act in this array now. Well, if our hash was take all the letters and add them together, guess what? Cat goes to 2 plus 0 plus 19 equals, I can do math, I just can't remember which letters are which or what number they are in the alphabet. So cat goes to 21. That would be its hash. That would tell us where it ought to go in our hash table. This is not talking about the array above. But act would go to 0 plus 2 plus 19 equals 21. So this is not a great hash function. There's going to be lots and lots of words that come out to be equal to 21. So we need to think of good hash functions. I'm not going to worry too much about that problem for myself tonight. I'm just going to think about if things can hash, then what do I do with them and putting them in the right places. So the other thing you can do when this happens, this is called a collision. Collision. When two things have the same key. So that's actually not the end of the world. It makes our hash table slower no matter what we do if we have collisions like that. But it's not the end of the world. So one of the things I could do is I could say, instead of having a hash table where like at index, so you'd have index 0, 1, 2, etc. out to 21, for instance, for our cat act example here, we would need to have at least out to 21. there are ways to deal with that too, but we'll deal with them in a moment. Let's say it at least goes out to 21. Maybe it even goes out to like 100 or 1,000 or 1,000,000 or whatever. So at index 21, we would love to be able to store cat. But crap, now we also have act that has the same hash value. So one solution is to just make a bucket there that can hold lots of values. So it could hold cat, and then when we see that act has the same hash value, that's not a huge deal. We can just make sort of a linked list or something there that will hold on to the next value, the next value, the next value. So that's kind of the simplest approach to handling hash-related things. We have something that conflicts, two things that ought to fill the same spot. That's okay. We just add some sort of linked list or some sort of bucket concept that we can get things from there. The problem with this, of course, is that once this gets to be too many things, so TAC also maps there. Yeah, I don't know if there's another one with 3 letters, but there are probably other things, like if I took C and shifted it to B, and yeah, you can shift the letters around and you could still get things that would add up to 21 in this scheme, this not very good hash example. So we could come up with ones where there are lots of items that end up fitting into this 21 bucket. And the more and more there are there, then the longer it takes me to find a particular thing that hashed to 21. So one solution is get a better hash function and be able to map to fewer or like more evenly distribute among the different spaces. For instance, if we had a hash function that paid attention to the index that a letter was at. 2 was at index 0 in cat, but it was at index 1 in act, then we could get better solutions that way. So that's one approach, is just get a better hash function. Find a better way to deal with strings. We could do something like 2 times 10 to the 0 plus 0 times 10 to the 1 and 19 times 10 to the 2, and so on. We could do something like this, and that would help to change it so it did not actually go to 21. I'm not actually sure what it would go to because I'd have to, 1900 plus 0 plus 2, so 1902 for that one. But that would give us, and then it would be a different thing here, right? Because 0 times 2 to the, or 10 to the 1, 2 times 10, 0 times 10 to the 0, 2 times 10 to the 1, 19 times 10 to the 2, so that would be 1920 instead. So we already see there that might be a better hash function. The other problem is going to be that we'll always have a limited number of buckets to fit things into, because we're going to base our array in this example on a hash table, we're going to base our hash table on an array. And so we could have an array of size 100. And if you take all the words in an English dictionary, for instance, there are going to be collisions there. No matter how good your hash function is, somebody's going to map to somewhere. Because usually what you do is, if you know your hash table is smaller than the number of possible values that might go into it, you just take whatever the hash value is for your data. So you hash your data, and then you do it mod table size. So we take whatever our size of our table is. For instance, here it was 100. And so any hash that comes out, like my 1902 and 1920 there, I might just take them and do mod 100. And that could end up badly for, say, 1902 and 1702. Those would both hash to something 02, which then when we mod by 100, we'll get back just the 02 part. So there will still be collisions because our table size is always going to be finite. We're always going to end up with multiple things that need to be put in the same slot. There are other more complicated schemes for this. I have a YouTube video or two about different schemes for making hash tables work well. But the first thing I'd love to do is to just play with a hash table and get this bucketing kind of thing working first. Get it to actually go into buckets for the different values that we've got there. So let's do this. All right. You know what? I'm gonna make a folder for this so that I can and I'm gonna take the current file and I'm gonna move it. Where'd I go here? And that way in my terminal, go to the hash table thing. Don't need these. Okay. So things that we're going to need. We will eventually need some kind of data that we can put into it. But let's just think about the structure of the hash table first. Okay. Brain's turning off. I need tea. I need tea in my life, and that will help the brain to do brain things. Oh yeah, it does. Okay. Keep some files open so that I can maybe steal some data from them or stuff like that if it comes around to it. All right. Okay, so some things we're probably going to need to do. Using namespace standard just to make things a little easy on ourselves. Probably at some point we're going to need to import or include, not in Python here, IOStream. Yeah. Okay. And then call it a hash table. Probably not the best of naming, but we'll live. All right. So one thing we know we're going to need is that in the private space, we're going to need some sort of array. Okay, so, and yeah, let's make, that'll be private. Okay. First things first, if I want to store stuff into the hash table, I probably want a structure that will help me to store that stuff. So let's call this an entry, and an entry will have int key. And let's say that entries have an integer that's a key and a string that's a value for now. We can try other data types and stuff. We could make it templated in C++. You're able to make like templates for what your class, what your data types will be. Let's go low key for now. Okay, so that's what our entries are going to look like. And so now we can create an array of stuff. Int table size, int used. We're going to need to keep track of how many entries are actually in the table right now too. That helps us do things like see how full the table is, which may be useful to us if we do any redistributing of stuff, like if we increase the size of the hash table. Okay. That should be enough for now. And let's do... So the entry is private. So what we want is a string. That's the value that's being inserted. Bool erase. Spacing is all off. So we want to be able to remove stuff from the hash table. Bool Oh, this is okay. How do we want to do this? That's fine. Let's so you know what? Here's a smarter thing to do. Let's do a type def data string. I think that's the right syntax for a type def. Okay, so data. All right. Yeah, my brain is thinking in like a Java type space where you would rely on your data type as having its own hash function. You'd probably do the similar thing in Python. In Python, you get the fun little underscore hash kind of thing that you can do. I'm trying to think of what would be the right... for now, though... Excuse me. Let's treat this as we're gonna include in the hash table. Int hash const data and v. Someone asks us to insert something. We'll call our tables hash function for now, In a better world, we would write a hash function that belongs to whatever type is being inserted there. But I'm not really wanting to mess with inheritance and the other stuff you'd have to do in C++ for that. So for now, the table's going to have the way to hash stuff. All right. Let's see. Oh, did I write that backwards? I think I did. It's typedef string data. All right. So, oh, I got stopped midstream there. All right, find, or actually, let's make this like a set kind of thing so that really all we're doing is we're checking for containment. Like, this could be something where we are like a dictionary, where we were seeing if certain words were real words. We could add words to the dictionary officially, but sometimes we want to query to see if they are a word in the dictionary or that kind of thing. Let's do that. Okay. Contains... Do I need to know this? Okay. What are some other things we might do for a hash table? We might have size, we might have stuff like that, but I'm not too worried about those for right now. This should give us a basic hash table. It's kind of more of a set or a dictionary sort of thing, where we're mostly checking containment and we can add or remove. But it should be, if we design it well, should be fast. The only other thing is, do we want our entry struct? So this is where what we could do is we could have entries point to other entries. Next, like have it be a next thing so we could step through everything in a bucket. I think that's a good idea. It seems like an idea to me. And actually then our entries don't need to store their key. They need their value, and they could point to the next one. So if you ask me if the word cat is in the dictionary, I can look at the first entry at index 21 in our previous example, and I could say, that one's not cat, but there's a next one. Okay, is that one cat? No, but there's a next one, and so on. And then I can quit when I run out, when I hit the null at the end, when the next is no more, when there is no next one. All right, so this would be a pretty simple hash table. I think this is just the header file. So let's clear here. GCC? G++ maybe. It's mad at me. Typedef. Does it not need a hashtag thingy? I don't think it does. I was thinking about pound define. Expected semicolon after class definition? Sure. I may end up just defining the class all in this one file, but we'll see. Data does not name a type. Did I get this backwards again? I don't write C++ classes from scratch very often, as you can tell. All right, you're mad at me still about data. Typedef data. Nope, the format is this. I just Googled it. Well, DuckDuckGo'd it. It's harder to say. That's why they're winning. Expected semicolon at end of member declaration. Yep, the struct needs a semicolon. Getting my C++ feet back under me here. All right, and then if I want to declare or define the actual, like give the actual definitions in the same file. I can't remember if I don't do the semicolon if I'm trying to do that, or if I still do it. You know what I probably also need is like a constructor, maybe? Seems like a thing you often want. Oh, so I'm like super old school C++, and I want to try to remind myself of some of the cool, neat ways that you can do stuff like can I just go like table size equals 0. Here, I'm gonna remove this and see if I can remember. No, it's colon, I think, in this. Used colon 0. Oh, and actually, let's start the table size off at something like 100. All right. Array equals entry 100. Do I have to do new there? I think I have to do new there. All right. And hash is a function. Don't need to declare that or define a value for that. Mad at me? Yeah. Interesting. How do we do that? I know I've seen myself do it with things recently, but I just can't remember exactly what the syntax is for it. Oops. Nope. Table parentheses. Feel free at any time to distract me with your questions, rather than whatever random tangent I get off on. You can join the queue, or you can type into chat if there's not a bunch of things going on. Function definition, yep. I can't remember what the syntax is for that. You know what? My research code has some. This is the downside of switching between languages so often, is you just lose those little details. All right. I know I did this just the other day. It's just not coming to me. There's like a particular syntax for saying, I would like to give this thing a value before anything happens. It's neat to be able to do. Okay. I got the colon in the wrong place. And the parentheses as well. Alright, here's what we do. Colon, table size, blah, used, blah. Will that do it? Hey, look at that. Alright, so now it's got a constructor, maybe not a perfect constructor, we'll have to see. But that should work. All right, and then we need a deconstructor, a destructor. And we don't need any of those. So ooh, we should be really thorough on this. I less than table size. I++, trying to avoid memory leaks here. So in C++, we have to actually think about the memory that we've used. If you've watched me do Python, you've seen me be lazy about this all over the place. So I have to actually step all through the hash table and clear out everybody in there. In this case, it will include not just the entries that are in that array, but also their nexts and nexts and nexts. Okay, so I equals 0, table size. If array I, then no, while array I pause, entry star temp equals array I equals temp next, and then delete, is it del? Delete temp? I think that's it. Okay. This will loop all through all the indexes of the array. That array of entries there. It will say if there's an entry at that index, then grab that entry and move the array to point to that entry's next. This may be null, and that's okay. We'll see why in a moment. But we want to delete the entry that was there. So in C++, we have to actually explicitly tell it to delete stuff when we're done with that stuff, or otherwise we get lots of stuff floating around in memory that we never can get our hands back on, and therefore clutters up our memory. So the reason that it was okay if temp next is null here is then array at index I will be set to null, and that will just mean that we quit our while loop here, because if array I is null, our while condition will say false, and we will quit our loop. Then at the end of it all, we will have cleared out the array. Is there a special, I forget, I can't remember if there's special syntax to delete an array. Delete brackets. That's right. Okay. Cool. Okay, so this is our bucketed hash table. You know what? I'm gonna be even lazier than I expected to be. I'm gonna just write it all into the header here. What is happening with my indentation here? Did something get screwed up? Something got screwed up. Bracket. Can we just select and like get everybody to, there we go. That's better. All right. And we'll even give hash an empty body. So they now all actually have implementations. No returns to, oh, cheap. All right, gotta make an actual stub there that returns something. Return false. Nope, stop. Return false. And the hash return 0. At some point, I'm going to want to write some nice little debug thing that lets me print out the whole table or something. All right. Could not convert while array I. Maybe because it's a struct? Interesting. I guess I could create like an empty entry at each one, but that seems a little overkill. Oh. Array should have entry pointers at each location. Okay. Because the first entry needs to be a pointer, so array I points to an entry, and then that entry's next points to an entry, which points to an entry. All right. So then they can be null or not null. All right, and this should be new entry star 100, and then we got a hash table, sorta. We can't insert into it, but we can create it and delete it. Okay. Let's think about inserting. So, you know what I'm gonna do to be super lazy is leave my hash just always returning 0 for now. And then that way, we'll get to see, because in the beginning it should just bucket everybody into index 0, and that should work fine. It will be extremely inefficient. It will be a linked list, in fact, but it will be written as a hash table. Okay, let's also create a void dump table that's gonna dump out our hash table for us and give us this basic structure will actually be useful for us there. We just gotta change one thing. Entry star temp equals array I right here. Here we go while temp, and then we're gonna go something temp equals temp next. Here is where we'll go cout temp value, was it? Elge and L. Okay. So here we're just gonna dump the values from the hash table. It was value. Yep. Okay. And in fact, what we'd really like to do is this. Dump out a bucket. And then, so we'll have like commas and spaces separating everybody within the bucket. There'll be trailing commas and spaces. I am not worried about this. And then we'll put an end L. In fact, we'll even output colon space, nope, colon space. Let's give us a main now so that we can actually see what's going on. Static int main, is that what we need? And I don't know if it's gonna get mad at me. I don't usually do everything in a header. I usually do separate files, but I'm being lazy here. Int argc char star. It's been a while. Star argv. Hash table h equals. Actually, I don't even need that. You know what? If I want to be smart, let's take a starting size for the hash table rather than hard coding it. Let's make a hash table with 10 entries first. H dot dump table. Uh-oh. Cannot declare. Oh, do I need? I don't even think I need static in here. I think I'm thinking Java stuff. No return statement. And we don't really need int there. Will it let me get away with this? I can't recall. Void main. Main must return int. No, it won't let me get away with void there. Hashtag C++ tricks. All right. Return 0. Insert. Oh, I deleted stuff out of insert and then didn't actually finish doing insert. All right. Dash O hash table. You know what I can do is I can just I think it's mad at me because it's a header file. All right. So now there we go. Look at that. It printed out our buckets. Nothing in them, but it printed them out. So let's make it so that we can insert things. All right. Int h equals hash k. Int end equals h mod table size. All right, so we can decide, I guess we'll be lazy on insertion. So one thing we could do is we could walk out to the end of the bucket, that linked list that's in each bucket, and insert there. Or we can just insert at the start and push everybody else back, which is functionally free in a linked list because all I have to do is this. Entry star E. Ooh, I don't have a constructor. Okay, entry star E. E dot value equals V. E dot next equals, oh no, can't do dot in C++ when we're working with a pointer, and we want to refer to its stuff, we need that little arrow. eNext equals array ind. So what this is doing is it's creating a new entry, and it's saying, I'm going to take that new entry, I'm going to make its next point to whoever is in my bucket already. You're in my bucket. I don't know why that's stuck in my head. It grabs that thing that's in my bucket already, and it sets it to be the next of this new entry. And then I'm just gonna say, now I will become the one who's in my bucket, right? I don't know why I'm getting so amused with that right now. Semicolon. So amused, I forgot to type a semicolon there. All right, so that should put it into that bucket. If there was nothing in that bucket already, its next is just going to point to a null, and that's okay, because that's how you tell that you're at the end of one of the buckets. So for instance, we should be able to do something like this. h.insert cat, semicolon, compile, e value equals v. V was not declared. What did I take that in? Oh, k. Why did I call it k there? That seems like a weird. It's gonna be the value. I think I was thinking of it as keys. I don't know. Who knows? No return statement. Yes. Okay. Return array next not equal. No. Basically, in insert, we're going to return whether something was already in that bucket. I don't know. Seems like a reasonable thing. Oh, you know what we should do actually is not that. We should check if the thing is already contained. Right now, contains is always returning false, so this is safe. So, if this contains v, return false, else return true down here. All right, that should be fine. If it's already in the hash table, then we shouldn't add it twice. That's not going to be true right now. If I add cat twice, it should work just fine here. This hash k. Oh, I did k in one place and v in another place. I'm going everywhere. All right. And should we write our hash so that it actually... Well, let's do this instead. Yeah, this is fine for now. Oh, core dumped. Did something wrong. eNext equals array end equals ha ha ha. Nope. E. I don't want to set array index to be equal to whatever it currently is. I want to set it to be equal to the new entry that I just created. Still wrong. So this should come back 0 because I just set the hash to always come back 0 right now. Then I create a new entry, I set its value. eNext equals array index, so this could be a null, that's fine. And then array index equals e, we return true. Alright, so let's make sure that I saved and compiled. I did. If I remove that, it should go back to printing our buckets. That's helpful. I'm assuming that the error is coming when I dump table. No. It's coming somewhere in here. Drink a little tea while I think about this. What is happening? Close out some windows, declutter my life for a moment. I did establish the array right there. I don't think I need to do this, but we'll do it just to be sure. Nope. Oh. Table size. That shouldn't be the issue. But that was incorrect. Yeah, that won't fix my issue here. I get the hash, which is always 0 right now. I then mod by table size, which should still be 0. Create that little entry friend there. Oops. There we go. I just forgot that in C++ I need to actually initialize things. I want Python back where I can just create a variable and be like, you exist. Okay, so I create a new entry, I add it there. Now we see cat is there. So if I go to insert some other things, act, bat, act, cat, these all map to bucket 0. And you can see that whoever was added last, bat was added last, is the one sort of closest to the left here, the one that we would access first if we were looking stuff up. All right, so let's do at least a bad hash. Int h equals 0. Let's see, int I equals 0. I less than Ooh, now I need to actually, C++. Have to remember how to do stringy stuff in C++. I don't usually do much string work in my, C++ code, because it's all researchy stuff. Pound include string, just to make sure I got all the right stuff. I is less than b.length. I++. I think this should work. If I do this, the code shouldn't, or the result should not change. Oh, we did get a seg fault there at the end. I'll have to look into that. Dump. Table seems to be seg faulting somewhere here. While temp. I less than table size. Okay, I'll look into the table or the seg fault there in a moment. Could be a seg fault in the deconstructor as well, somewhere in there. Could be any of the above. Delete temp, delete array. Let's see if that fixes it. One of these was an array. The other one was not. Don't delete non-arrays like you delete arrays. It's not good. I would go so far as to say it's bad. Okay. Insert is a thing. Okay, contains should be easy. So we basically just have to do the reverse of inserting. And then we have to loop through. So we have to get the hash for it and then loop through. But first, let's do this. I have to remember how to get a specific character from a string as well. Can I use them just like arrays? I can't remember. Yes, I think so. Oh, that's if it's a character array style. I don't know if I can get away with this. We'll see. C++ does have some nice features. All right, h plus equals vi. Let's see if I can get away with this. Hey, look at that. Act and cat map to 2. Bat maps to 1. And, you know, that's because these two have the same sequence of letters, just reorganized. And so, yeah, that should be fine. I'm going to remove those trailing commas because they bother me. And temp next if temp. Basically what I'm doing is I'm stopping the while loop one step earlier when I only have one item left. Then down here, if I have that one item, then let's just print it and not a comma space. There we go. Bat, act, cat, etc. I'm sure there are better ways to do this. If you have a suggested better way, let me know. Share your ideas. Okay, contains. So contains should be pretty similar to this, except it stops here. All right. Int entry equals array end while e equals e Next, okay. E if e dot value equals, not dot, arrow, equals v, return true. Else, if we get out of this for loop or this while loop here, then we're going to return false because we looked in the correct bucket for it and we didn't find it. All right, so here's a test for us. Before I do this contains, let me comment out all this stuff. There's nothing stopping me without that contains. There's nothing stopping me from entering the same value multiple times. Act. Yep, see? Act, and then cat. But once I fix contains to actually do a containing, then it will tell me this is already in there, so that in my insert, I will say, nope, already had it. I'm not going to be adding that right now. And we see we're back to only act and cat. So we can quickly check if something is contained, and we can quickly prevent ourselves from adding duplicates to it. All right. So erasing. That's the last bit for us to have an actually functional hash table-y thing here. It's a strings only hash table. It's got a bad hash function. There's lots of complaints we could make about it, and that's true of any data structure. But it's a hash table, even without erasing. It's kind of a hash table, but let's do it anyway. So here's what we need to do. We need to look where the thing would have been. And then we'll do a similar loop here. Yep, probably want a new line there. All right, for now. So if we erase it, we're going to return true. We're also going to want to actually erase it. So if we found the thing, we want that thing removed from our list. Ooh, it's snowing outside here. So what we're going to need to know is we're going to need to know who came before it, so that we can tell whoever came before it, now you should pass by me, don't actually point to me. We also will want to do some deleting in here too. Last thing we want to do before we return is delete E. And then, so here's what we need. We need entry star previous equals array end. All right. While previous if it's the first one in the array, okay. We've got some special cases to handle here, I suppose. Yeah. If it's the first one, or not in the array, but the first one in that little linked list, then we gotta do something different. All right. So, E equals previous next. If E value equals V, then previous next equals E next. Delete E, return true. If previous is value, Is there a cleaner way to do this? There might be. That's okay though. For now, this should work. Previous value equals v. Then if prev and, I want to make sure that it's actually not a null there. All right, then this equals prev next. We delete prev and we're done. All right. Yeah, this is fine. I'm sure there's a cleaner way to handle this special case, but it's not the end of the world. So for instance, out Vandal. That's wild. Nope. What is happening? What have I done? Right. Also, I could just copy and paste. All right. Look at that. So here's the original table. It has bat, act, cat. And then we removed cat, which put act in place there. We could remove act and put bat there. Yeah, we can do lots of things. Oh, you know one thing we didn't do is when we inserted stuff, we didn't increase our, what was it, used? I think we had some measurement for how many entries were in the table. I suppose it's useful. If we're gonna have the thing, then we may as well make it. And then same here. Used minus minus. Used minus minus. Okay. So now it should track how many spaces are actually used. Neat. Okay. It's a pretty simple one. Let's see. What else could we do? I could make a better hash function. And I could make it resize. Those are probably the other two things that I could reasonably do. I mean, times what is the, there's a power function that I can't remember. I think comes from math.h. Yeah. So I could do that 10 to the power thing if I wanted to. Pow 10 I. It's not going to be perfect, but it'll be better. You can see they all get a little spread out there. And this is only 10 slots, but you know, I can add more words to it too. All right, let's reduce the redundancy there. Sat, ban, bar, bet, cot. So you can see with 10 items, it's still, you know, they're kind of, they get clustered still. No matter what we do, they're gonna kind of. The far fan, or 10 slots rather. Yeah, not the worst distribution, but certainly not the best either. Strange that all of those are ending up. Oh, because I'm doing that 10 to the power thing. So I think they're getting filtered by what letter they start with. Oh, that's interesting. So you'd probably be better off going, well, yeah, lots of other possible combination schemes and good hashes for strings. This is definitely not the best of them. For example, we can do some with like prime numbers. Yeah, there's lots of possibilities. Also, you get real big numbers real fast, but you could also multiply instead of add the numbers, stuff like that. Let's see. Yeah, what else can you do? Oh, wait. Okay. Can't remember. Will this just make it classified by the last letter? Ooh, that's taking a while. What did I do? H times that power plus VI. Why it's taken so long after that. Yeah, that just classified them by the last letter. Not as helpful. All right. Anyway, and once I got more than 10 slots, I would end up getting a lot more distribution for these. You notice, oh, they're still a little clustered. That's sad. Barband bat. Interesting. Oh, first two letters. B-A. B-A. Look at that. Do I get other? Yeah, bet ends up in a different place. So this is not a beautiful, amazing hash function, but it's something. And then... Actually, I think it may be worse than the other one in some senses, because at least that one was not just classifying on a single letter. Once we got a big enough hash table, if we had one that was like 1,000 entries, yeah, it wouldn't be the end of the world. They'd get distributed around based on the first several letters or stuff like that. But this is just fine. This works just fine, actually. Yeah, way better distribution. Okay. So the other thing that we could do is we can make it resize. Do I want to do that? I don't want to make it a thing that a user could do. So one thing you might do is like just double table size. So you could say new int new size equals table size times 2. And so that way you end up with twice as many slots, and you know, if things overfill, then you can have it rehash and redo everything. You could have it rehash based on a couple of different criteria. One criterion would be, say you make a limit on how long the buckets can be. You could say, I just don't ever want them to get to be more than 10 items long. And so you just keep rehashing until they're not 10 items long. The other way you could do it is you could say a percentage of the table that's filled. If it's more than 50% of the number of slots, then you could double the size of the array, hoping that more evenly distributes them. Regardless, rehashing will look a lot like our original hashing. It's just we need a new array, and then we also need, and this is where what I should have done is have, void clear. So let's write this clear thing so that will clear out the current table. The only trick is I don't really want to delete all those entries, do I? Okay, we'll duplicate the code. It's not the end of the world. So our rehash will first look a little bit like our our delete, because we need to make sure that we clean out that original table and bring everybody over. Okay. And then delete the old array and then swap in with a new array. So entry ** new array equals new entry * new size. All right. There's two ways to do this. Actually, I'm gonna do it the opposite direction. Equals array. We're gonna make old and hold on to the old stuff. Here's why. Old size equals table size. Now, table size times equals 2. So now we're doubling the size of the table. Then we're going to create our new array. So array equals entry * array table size. So this is so I can be lazy, and I can just call to insert this. So what we're going to do is we're going to take that loop that went through and deleted our stuff before, but instead of deleting this, insert. Oh, yeah, that's fine. That's fine. So it'll have to redo the hash and stuff, which is not the friendliest thing, but I have an idea. Put into array. All right, insert will be public, but insert's gonna have a portion. Okay. This put. Pause one moment. Maybe I'll duplicate code again. Or I can just have it redo the hashing. I don't love redoing the hash because some hash functions are expensive to do. This is not the end of the world, but yeah, it'll have to redo the hash anyway, won't it? Yeah, it'll have to redo the hash, duh, because the table is a different size. Okay, that's fine. So we'll just be lazy. And we'll this insert temp value. Oh, which does mean that we can delete temp. Okay. And then at the end, we're going to delete. Oh, so here's the tricky part. Old array I. Old array I. Oh. Yes. So we're pulling things out of old array. And we're also using old size here. So this is all going over the old array. It's grabbing stuff from it. It's then going to insert that into the new array by using the insert function. And then it's going to delete the stuff that was held in the old array. When it's all said and done, it's going to delete the old array. The new one will be the new thing, and it's going to be beautiful. The other thing that we should do is we should make sure that as we're grabbing stuff out, that we're balancing out. So insert is going to increase the number that are recorded as belonging to the array. I think we called that used. So let's reset used to 0 when we create that new array. All right, let's make sure this compiles, because it's very likely I screwed something up. New. There we go. All right, and then let's have it rehash if a bucket gets more than one item in it. Is that fair? What's our largest bucket so far? We got 2. Let's add some more stuff. Fax. Fox. Box. Tax. Why am I stuck on 3-letter words? I don't know. All right, so what we're going to do is we're going to rehash if a bucket gets more than 4 items in it. I don't know. There are lots of ways you can judge this. Like I say, one of the ones is you could count how many buckets are in use and say, you could say if the number of items that you have is double the size of your array. Actually, let's do that. Let's go when it's double the size of the array. And this way, I can also trigger that and show the thing resizing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. Let's reduce the size of our array. That'll cause tons of collisions, right? They're all jammed into 5 slots. 1, 2, 3, 4, 5. Oh, one of these is a repeat. Let's remove the repeat. We've already got that tested that it's not adding duplicates. 2, 3, 4, 5, 6, 7, 8, 9. So these. All right. I'd like it to some of these tests for, I won't remove them, but I'll comment them out. Alright, so we get 5, 6, 7, 8, 9 items there. And then we're going to say if the number of items inserted is double the size of the array that our hash that's backing our hash table, let's resize and rehash it. So in insert, where are we here? It's getting too long. I'm actually doing interesting work. All right. If used plus 1 is greater than table size times 2, rehash. We'll rehash and then we'll insert the new thing. Really shouldn't matter, but it saves us doing some work of reinserting that one. Oh, and it should be this rehash. All right, so instead of just jamming more stuff in here, it should actually double the size from 5 slots to 10 slots. Let's see if it does it. I see 10 slots. That's promising. 5 slots. Then we insert something. Bitband, the got, act, cat, sat. Oh, far. Far was what got inserted. So I guess it didn't rehash right here. Why? That's 5, 6, 7, 8, 9, 10. Used would have been 9 at this point, and 10 right here, right? Well, I mean, it would have been 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so it should have been 9 here by the end of inserting whatever the last thing was that was inserted here. That means when I insert far, it really should be resizing. Well, okay, but the moral of the story is that at a point, when it gets too full, it resizes, which causes it to redistribute. So now we only have at most 2 items. We have no guarantee that we'll have at most 2 items, but we have if we have a good hash function, it's likely that we'll have at most 2 items. And you can see they're kind of cramming in again here. And soon it would probably resize again. We could add some more and have it resize again. Let's find some more words that we can fix. Six. Fit. Is that enough? Not quite enough yet to get it to resize, is it? Fin. Fib. Really stuck on 3-letter words tonight. Don't know why. I need 20 to be in there. Well, 21 it looks like. I don't understand why. I'm still not sure why it wasn't resizing quite at the spot where I expected it to. Used plus 1. So it would have been 9, that'd be 10. Greater than or equal to. There we go. Those will get you, friends. Okay, now it has resized, so let's do this. Let's steal this stuff and have it only do the last one there. Yeah, so it had, oh wait, there's some like missing spaces here. Did we dump a table? Yeah, there we go. We need some spaces between those. Okay, so we started off with 5 slots, then we overfilled it, and it says let's redistribute, and makes it 10 slots. Then we add some more stuff, And you can see that it's not it's not resizing each time, which is good because resizing is a costly operation. We don't really love to do it, which is why we do crazy things like double the size of our table each time, because we really want to avoid resizing the hash table if we can, because that means that one insert took reinserting every single entry in the hash table, which is why there are other schemes for handling hash tables as well. But this is a resizing hash table. So we get here, we had 10 entries, we insert fin and fix and some other stuff, and we get pretty darn full. You can see we're getting longer lists on there, linked lists on there, bigger buckets. And then we insert one more, and it pops us up to 20 entries, and you can see the buckets have redistributed a little more. And it would keep doing this on and on and on the more things I added to it. So that's a pretty full-featured hash table there. The weak points on it are, again, it doesn't have a great hash function built in, but honestly, a hash table really shouldn't be doing the hash function for you most of the time. Most of the time, your objects that you're inserting should have some notion of their own hash function. And then they should give you a number to say, okay, I hash to 2156832 or something. And then your hash function should take that and do this modding to put it in the right index and stuff. So I don't feel bad about having a bad hash function, because that's not really my job usually when I write a hash table. And then the other weakness would be this one's hard-coded to only work for strings. But we could pretty relatively easily give it a templated type here and have it take any old type of data. We would just need to somehow make sure that data did have a hash function of some sort. And so that's where we would get into possibly weirdness with the class hierarchy to guarantee that it inherits from some class that guarantees a hash function or something. And that I don't want to mess with tonight. So we got a hash table. It inserts, it removes, it erases, it can check containment and should be checking that pretty quickly. We could do like 1,000,000 contains checks on random values and see how fast they come out if we really wanted to like profile this and get a good feel for it. We can print out the whole hash table and see the different buckets that things are in. And it's even got some stuff behind the scenes to resize and redo the thing if it gets too filled. And again, you can choose your criteria for rehashing. Resizing a hash table is referred to as rehashing because when you change the size, that changes the buckets, which means that you will have to, as I had to conclude for myself, you will have to relocate where things should be in there. So that was kind of fun. I haven't written a C++ hash table in quite a while. As I say, for my research here in the near future, I'm going to have to probably write a fancy specialized hash table that has at each slot in the bucket its own bucket of things. It's going to be a wild ride. I don't know if I'll end up coding that on stream or if I'll do that sort of offline, because I am bold enough to make mistakes in front of y'all, but there's a limit. There's a limit to it. But yeah, there we have a hash table. Not the most efficient hash function, and still always room to add on to it, always room to do different cool things. There are entire other schemes for hash tables in which instead of having these buckets, you just try to find the next empty slot. So if we looked at some of our early things, when we were looking to insert a word, if we found that its slot was already full, we might just keep looking, knocking on doors until we find an empty spot. Those require exciting, fun math to try to find where someone moved to. It's kind of like the post office when you have to do your, your change of address sort of thing, because it expects you to be at slot 1, but you actually had to walk down the hash table a bit to find an empty spot. There's all sorts of wacky and fun other schemes. On my YouTube channel, I have some videos that you could take a look at that talk about some of those other hash function, like collision handling schemes and stuff like that. They're really cool. I love seeing the different approaches and thinking about the different possibilities of like, okay, well, this one offers me this guarantee, but I lose this other guarantee that I would have gotten from another one. So check those out if you're interested. Otherwise, I'm going to call it a win. We made a hash table. It is able to do those quick hash table lookups, because the beautiful thing, and I guess I underemphasized this when we first talked, but if you think about like an array where I don't know what index things are going to live at just based on their data, or a linked list where I might have to hunt through every step, a hash table doesn't have to do those. It can tell where somebody should live very quickly based on their data. It takes the data, it calculates this cute little hash function, and then it mods it by the size of the table, and that's where that thing should live. Now, that's the perfect theory, that you should be able to just find one thing right there. As we saw, in practice, we sometimes lose a little bit of that. Like, we know where the word fib should live because we do that math of like what the F character adds up to, what the I character adds up to, and so on. We know where it should live in bucket 5, but we may end up having to look through a few different items on the way there. If we limit those buckets to a maximum length, and we say, once they get to this certain length, I'm just going to rehash everybody and resize the thing, then we do get technically constant performance for lookups and things like that. We get technically constant performance for lookups because we're saying, I'll never have to look more than 3 slots in, or that kind of thing. So we have a working hash table. I'm pretty happy with that. Yeah, the one I'm going to have to write is going to be a lot more complicated for the research code. But this was good practice to get back into how I would do some of this stuff in C++ and how some of those hash table quirks can work. So, I saw we had a new viewer join. If you have a question and you're interested in asking about something or bringing up a topic, I've got a little extra time. I can stick around. So feel free to ask in the chat. Otherwise, the thing that I've been poking at during most of the time this evening has been this hash table in C++. And that's been pretty fun. And yeah, so I'll stick around. I'll sip some tea for a moment. And you can ask a question if you got one. Say hi. And we'll use a little more time if we want. The tea has gotten cold, but luckily it's a brand that still tastes all right when it's cold. I hate when it gets all bitter. Oh, and likewise, if you have topics that you would like to suggest for future times, feel free, because what I'm thinking I'll do is I'll come here with a topic in mind. I can put that as the title, the description and stuff for the stream. And then if people ask questions, I love to be derailed by those when I'm not like intensely doing something for, research or that kind of thing. So feel free to share questions that you have, ideas for future topics, anything like that in the chat. And if you joined a little late, check out the video. And as I mentioned a moment ago, you can also check out my YouTube channel, which is, you can do the, here, I'll do it. You can do YouTube command in here, and it will show you the link to my YouTube channel. I've got videos on hash tables. I've got videos on linked lists, lots of different data structures, algorithms, particular programming language videos. And yeah, bring ideas. If you haven't already followed, follow. I will probably be streaming some research code on Wednesday afternoon. I think is going to be the plan. It may or may not be the super intense hash table I've been mentioning. We'll see. And I've been trying to stream some like intro CS examples that I use in class. And then tonight I had a request for a hash table, and I need to write a hash table for research. So it was perfect synchronicity. So I think if nobody has any thoughts, questions, anything they want to share, I'm going to head off of here. And I will be back around. I'll be back around at least Wednesday, maybe tomorrow night too, if I've got an interesting topic or if I'm just feeling like doing something extra. So it's been lovely. Hope you take care of yourselves. Follow, check back around, bring your questions, your thoughts, your ideas. I want to hear how you do things and how you're learning things, what's going right and what's going wrong for you. Otherwise, have a lovely evening.